All right, so I said I'd do some practice questions, and whoops, this is my phone. Let me turn that down. So what we have here then is practice C, D, E, and F, and these are K formula practice questions. So I'm going to go ahead and work out some of them. One I got asked a lot about in class was practice C number 3. It says a driver in a car is traveling at a speed of 21.8 meters per second. So that's going to be our initial velocity. Something I usually do with all physics problems is I do a drawing first. And so that's usually a good idea. And it gives me a chance to jot my variables down as well at the same time. All right, the driver sees a cat, which is 101 meters away. So I don't know if I can draw a cat. Okay. Okay, so there's a cat in the road, and the driver's going to come to a stop at before the cat, right? At 99 meters away. Okay, and how long will it take for the car to accelerate uniformly to a stop in exactly 99 meters? All right, so to a stop. This means that when we travel 99 meters, that our final velocity is going to equal 0 meters per second because we saw stop. When they say accelerate uniformly, we don't know what the acceleration is. But the fact that it's uniform, let me close this side part. The fact that it's uniform means that it's the same. So it's constant. All right. So that's what we're working with here. Okay. Coming back up here to the 99, the 101. The 101 really doesn't matter, right? So what matters here is the 99, and we're going to call that delta x. Okay, so let's see if we have all of our variables then. We have VI, VF is 0, VI is 21.8. Acceleration we don't know. Delta x is 99. I feel like we're missing one, and that's time. Did they tell us time? Let's see. No, how long will it take? So this is what they're asking. How long will it take to make this stop? So we want to know time, right? We don't care about acceleration. We don't know it, and we don't want it in our formula. So ideally here, we'd pick a K formula without acceleration in it. So if you have your K formulas in front of you, the one you would choose is the one that doesn't have acceleration, which is K4. K4 looks like this. Let's go ahead and plug in what we know. I'm going to go ahead and write the units. I don't think it's too big of a deal. I think our initial velocity was 21.8. And we want to know t. All right. So 0 plus 21.8 is just going to be 21.8. So we really don't have to worry about that 0 there. Half of 21.8. What is that? It's 20.9. Yeah. No, I mean 10.9. Jeez. 10.9. Okay. So we're going to multiply that 10.9 by t and get 99 meters. So we'll just divide both sides here by 10.9. Notice the units on it are meters per second. I got to make sure I'm writing those. Okay. So 10.9s cancel, meters per seconds cancel on the right. We're left with just t. The thing I want to point out is on the left side, you have 99 meters, but you have this fraction hanging out on the bottom. So when that happens, you got to multiply by the reciprocal, right? So we're going to multiply the 99 meters by 1 second over 10.9 meters. So what I'm saying there is then that the meters are going to cancel and we're going to be left with seconds, which is the unit we want. So 99 divided by 10.9, whoops, is equal to 9.08. I don't have the answer key in front of me, but I believe that that is right. All right, good. Okay, let's go ahead and move on to the next practice and do one from practice D. All right, so practice D, the problem we're going to work out is number 3, and it says a car starts from rest and travels for 5 seconds with a constant acceleration of negative 1.5 meters per second squared. What is the final velocity of the car? How far does the car travel in the time interval? Okay, so car is starting from rest. Let's go ahead and draw this. So I'm going to have the car facing left, and I'll point out why here in a second. Okay, so its initial velocity is 0 because rest, right? When you see the word rest, that means it's starting from 0 meters per second. It travels for 5 seconds, so there's our time. With a constant acceleration. Now this acceleration is negative, and that means it's going to be speeding up at negative 1.5 meters per second every 1 second. So in the first second it'll be going negative 1.5, or after the first second it'll be going negative 1.5 meters per second. After the second, negative 3 meters per second. After the next second, a negative 4.5 meters per second, and so on. So we write that as negative 1.5 meters per second squared. All right, good. And what else do we know? What is the final velocity of the car? How far does the car travel? Ooh, okay, we want to know both. So we're going to find VF first, and then the second thing we'll do is how far the car travels, which is delta X. All right, so something I want to point out, right, is that with this negative acceleration starting from rest, we are going to be speeding up to the left. So, so what I'm saying here is the acceleration, sometimes I like to draw it up here, is equal to negative 1.5 meters per second squared. All right, good. And so we want to know, what is this VF, right? At some later time, the car is going to be moving down the highway, moving down the road, and it's going to have some VF, and we want to know what that is. All right, so what formula should we use? Let's look at this. We know VI, we know T, we know A, and we want to know VF. So we want a formula without delta X. I think this is going to be K1, which is usually my favorite formula to use because it's the easiest one. Oops, there we go. So I'm just going to go ahead and write K1 up here. VF is equal to VI plus AT. So notice how, like, what is missing, right? Because there's only 5 variables. And the one that was missing, I'll highlight it here in green. This is the one that kind of determined what formula I was going to use or what I was looking for, right? Because I just didn't want it in there. I was like, what formula is going to not have delta X, right? And then I can work from there. Obviously, I want delta X, but I don't want it for this part. I want it for the next part. So I'm going to go ahead and plug these in. Don't know VF, know VI is 0. Know that the acceleration is negative 1.5 meters per second squared, and the time is 5 seconds. Notice that one of these seconds on top is going to cancel the squaring there. So we'll be left with meters per second. What's 5 times 1.5? I think that's 7.5. Okay. So negative 7.5 meters per second. Oops. Okay. And that's it. All right, cool. All right, now let's go ahead and get delta x. So we have a lot of different ways to get delta x. I think I'm going to go K2. It doesn't really matter. We know every other variable, so we could use K3, we could use K4 like we just did a second ago. I don't think we've done K2 yet, so let's do that one. All right, so K2 says delta x is equal to VI. Ooh, that V looks pretty bad. Looks like a gamma, actually. All right, delta x equals VI times T plus 1/2 AT squared. Only the T gets squared. Something important to note is that this has delta x way over on the left, but you don't have to start with the variable on the left to solve for it, right? I could use this formula and solve for VI. I could use this formula and solve for T. I could use it and solve for A, right? It doesn't matter. All right, let's go ahead and plug in what we do know. I believe we're starting from rest, right? Whoops, as I write 1.5. Starting from rest here, so 0 meters per second. Time was 5 seconds. We're going to add it to, I think this was a negative 1.5 meters per second squared. And the time is 5 seconds, which we have to square the 5 seconds. So obviously this term right here, just going away, right? 0 times 5 is going to equal 0. So that can just, we can get rid of that. So we're left with delta x is equal to 1/2 times negative 1.5. Well, I think I know what 1/2 times, isn't that negative 0.75? Yeah, let's just write that. Negative 0.75 meters per second squared. 5 seconds squared is 25 seconds squared. So square the number, square the units. Now we can see cancel off seconds squared. 25 times 0.75. I don't know what that is. What's 3/4 of 25? Ooh, it should be about what? I don't know. Half is 12.5, so about 12.5 plus another 6 is 18.5 plus 18.75 maybe. All right, let's see. I'll just type it in the calculator. Yeah, 18.75. Okay, so we'll just go ahead and multiply that, and that's fine. But we do get a negative 18.75. And notice the units are meters, right? This is how far the car went. So this isn't the distance. This is the displacement the car went, right? The car traveled, you could also say 18.75 meters left, right? Assuming that left is negative, that would also be an acceptable answer. Usually when you do these problems, you always want to write, if it's not, because it's not always obvious, you want to come up here and write, well, left is negative and right is positive. And then that way we know that that's the case, that negative means to the left. What else can we say there? I think that's about it. Did they ask for displacement or did they ask for distance? If they ask for distance, we'll just make it positive. How far does the car travel in this time interval? Usually that does. How far is usually distance. I'm not sure what the answer key has. I'd be interested to know if they're being sticklers about it and expect you to write distance. So you could just say 18.75 meters if you want distance, and displacement would be negative 18.75 meters or 18.75 meters left. All right, that's it. All right, good. Let's go ahead and go to practice E. I think in practice E, we're going to do questions 5 and 6. All right, so practice E number 5. Aircraft has a liftoff speed of 33 meters per second. What minimum constant acceleration does this require if the aircraft is to be airborne after a takeoff run of 240 meters. Okay, so let's think about what this is saying, right? An aircraft has a liftoff speed. All right, so this is the speed required for it to get into the air. And there's going to be, we want to know the minimum constant acceleration of the aircraft to be airborne, to become airborne after a takeoff run of 240. So the aircraft, the plane, is then going to, so what we're saying here, let me see if I can draw this. It'll look like a space shuttle. All right, so the plane, which doesn't have any wings, the plane is going to is going to take off at that speed, is what I'm trying to say. So liftoff speed is 33 meters per second. So initially, the plane's going to be going 0, right? And this is always the hardest part, right, of these problems, is getting the information together, right? Understanding the hidden rules in some of these problems. Yeah, I mean, this is way tougher than the actual algebra. So if this is what you're struggling with, I hear you. That makes sense. That's right. That's where most students struggle is the first part. The first part, this part requires the logic and the thinking, requires the experience of doing these problems, requires understanding what the hidden rules are, what the, what rest means, what figuring out what this problem is saying, because it's not written very well, I don't think. So this is definitely the tougher part of the problem. All right, so now that we understand that the aircraft is going to accelerate along this runway, right, some minimum acceleration, right, because it could accelerate any rate, but we want to know what's the minimum. So, and it's a constant acceleration. So I'm going to write, equals question mark. That's what we want to know. We also know what liftoff speed is 33 meters per second, so that's going to be the final. So right here, so that's the VF that's going to be required. We're going to, of course, call positive to the right, negative to the left. And I think that's all we know. Oh no, we know the runway is 240 meters. Okay, we don't know time, so I'll just write that down. T equals question mark, and this distance right here, this delta x is equal to 240 meters. Okay, I think we're good. So let's look at this. Let's get the highlighter out. So we want to know acceleration minimum. Did I not write an x next to that delta? I'm sorry. All right, that's not much better. Let me just erase that. There we go. Okay, delta x is 240, VI is 0, VF is 33. So we want something without time. The best formula without time, right? Because we don't know time, and we don't care about it. They don't ask us about it, so we don't, yeah. The best formula without time is always K3. So K3, let's write that down, is VF squared is equal to VI squared plus 2A delta X. Okay, let's go ahead and plug in some values then. 33 units are getting squared along with these numbers. VI is 0. So that's an easy one to square. That's just going to be 0. 2 times, we want to know the acceleration, this A min. Delta X is 240 meters. All right, so let's get rid of that. That's 0. We don't care about that. 33 squared, I have no idea what that is. 30 squared is 900. I don't know if that helps. 1089. All right, so I square the units too. 2 2 times the acceleration. Well, let's just write 2 times 240. 2 times 240 is 480. Don't forget your units of meters. And that's all going to be times acceleration. All right, let's divide both sides by 480 meters. Get the A alone. That's how you know what to divide by, obviously. When you have fractions like this guy, let me show you, hanging out in the top of your fraction, it's really simple. When they're on the bottom, you have to multiply by the reciprocal. That's where life's difficult. But when they're on the top, just bump whatever's in the bottom to the bottom, and whatever's on top stays on top. So I'm saying that the meters squared can stay, and the second squared just goes down here, or is all that's going to happen. So let me write that then. So 1089 divided by 480. I'm going to use a calculator for that one. 2.268. So maybe 2 points. Okay, so let's go 2.27. And we're saying that the meters squared stays. On the bottom, we already have a meters hanging out down here, but now we have our second squared down there. Let's finish writing this, and then we'll cancel some of those off. Is all equal to the acceleration. So units should be meters per second squared. Let's see if they are. Cancel the square meters with one of the meters on the bottom, or the meters on the bottom with one of the meters on top, and you're left with meters per second squared, which is what we expect, right? So I'll just write it again just to clean it up a little bit. Acceleration is equal to 2.27 meters per second squared. If you want, let me put a box around that. If you want, let me see, you can write that, right? And just so I'm being clear about this, acceleration is a vector, right? It points. So you could have wrote that as 2.27 meters per second squared in the positive direction. You could have wrote that as 2.27 meters per second squared to the right. You could have wrote that as 2.27 meters per second per 1 second. All right, so all of those are correct. Oh, dang. I was trying to highlight, and I end up grabbing the yellow marker instead. So all of these are the same thing. Okay. All right, good. Let's do one more. Practice E number 6. Certain car is capable of accelerating at a uniform rate of 0.85 meters per second squared. What is the magnitude of the car's displacement? So I want to know delta x as it accelerates uniformly, a, but we don't know what a is, from a speed of 83 kilometers per hour, 8 kilometers per hour. We need meters per second. These units have to agree. This has to agree with this. All right, so we're going to get it to be meters per second. From a speed of 83, so this is going to be VI, to this speed. This is going to be VF, and this is going to be A. We want to know displacement. We do not know about time, all right, and nor do we care about it. So we want to find displacement, which is delta x. So what formula? Right away you should say K3 because we just used it, right? Where time isn't necessary. You don't even have to know it, and we can just solve this problem. So let's come down here. I already forgot a lot of those numbers, so, and I didn't draw it. Maybe I should do that. Yeah. And it's starting at initial speed. Okay, so I think what we have for this drawing then is a car that's traveling, whoops, not to the left, keep it to the right here, at some initial velocity. and then speeds up. And has some acceleration, which is also directed to the right. Let's go get those numbers. 0.85 for the acceleration. And those other two, which are obnoxious because they're in kilometers per hour, 83 to 94. And we want to know delta x. Okay. We don't know time, nor do we care about it. So, okay. So let's, before we get K 3, let's go ahead and change those units, right? So 83. Oh. 83
I didn't get that. Could you try again?
I don't ever use Siri, but it always, I don't know. I don't know how to turn it off. All right.
Sorry, I couldn't quite hear you.
Okay.
Could you please repeat what you said?
So we want to get to meters per second. So we're gonna say 1 hour is equal to.
I didn't get that.
Oh,
Could you
jeez.
try again?
All right. Hopefully, I'm just gonna put it. Okay. All right. 1 hour is actually equal to 3,600 seconds. I'm gonna speed this up a little bit and use that. 60 seconds in a minute, 60 minutes in an hour. So 1 hour is actually 3,600 seconds. I didn't use that conversion factor a lot in the last chapter because I was trying to keep it a little easier, but I want to speed this up. So, and we might get from kilometers into meters. We know that 1 kilometer is equal to 1,000 meters. Let's go ahead and do some canceling there. Okay. And we're left with seconds on bottom and meters on top, which is what we want. So we are done. Let's gather up everything we have. Maybe I should do that underneath just so it looks a little bit better. 83 times 1,000 times meters. On bottom, 3,600 times seconds. And that's good. All right, let's go ahead and plug that in the calculator here. 23.06. And that's going to be meters per second. All right, so now we can do the same exact thing for the other one, right? So once again, what was the other one? 94, I think. And same exact work as before, right? Do it a different order this time. Cancel off kilometers. And we're left with meters on top, which is what we want. And then on the bottom, we know 1 hour. We'll put it on top so we can cancel the hours on bottom. Is equal to 3,600 seconds. Cancel your hours. You're left with seconds. Gather everything up. Could I have just wrote the same fraction as above with a 94 instead of an 83? Yeah, I could have. But I was just being difficult. It's good practice, especially if you haven't done it in a little while. All right, so let's go ahead and plug that in the calculator. 26.11. Whew. All right. So there's our VF, and here's our VI. We are going to be accelerating. All right, so I'm running out of room here. Let me get another page here. Okay, so I think we said we don't know time, we don't care about it, so we're going to use K4, or K3, sorry. All right, let's go ahead and plug in what we know, 26.11. Square it. VI is 23.06. Acceleration, ooh, and I'm running out of room, dang it. I think it was at 0.85, yeah, 0.85. And we're solving for delta x. I'm going to try and squeeze this in here. I don't know if you can see that really well. I apologize. Looks like that, and this can go away. All right, so that's the end of it right there. All right, so let's multiply here. I think 0.8, what is that? 0.85 squared, that's 1.7, right? Or 0.85 times 2, I'm sorry, is 1.7. Okay, so so what I'm trying to say is, let's put this in our calculator. 681 meters squared per second squared, square the units too. 531.76 meters squared over second squared plus 1.7 meters per second squared times delta x. All right, we'll subtract this 531, right, 0.76 meters squared per second squared from both sides. Notice that the units have to be the same in order to make this subtraction happen. Otherwise, you can't do it. So that's kind of interesting to see. All right, so obviously these two are going to go away. I'm left with whatever that is, 681.73 minus second answer, 149.97. Whoops, why am I still in red? And this is meters squared per second squared is equal to 1.7 meters per second squared times delta x. All right, pretty straightforward here, just divide by 1.7, but I'm also going to divide by the units just to show you that, right? Those two cancel, these two cancel. We're left with delta x. Over here, divide by 1.7 meters per second squared. So we have to multiply by the reciprocal again, right? There's a 1 down here. So what it's going to look like, I'm just being as difficult as possible right here, but it's good practice just to show you what's going on mathematically. You have meters squared. We said this fraction, let me point this out too, that the meters, that for this fraction, this can stay. This has to go to the bottom, right? So that's just for the top of the fraction. We haven't even looked at the multiplying by the reciprocal yet. All right, so that's what's going to look like right there. But now we're going to multiply by the reciprocal of the bottom. And so the bottom is this. The reciprocal of that would be 1 second squared over 1.7 meters. Okay, so now we can start to see that a meter on bottom is going to cancel the square on top. The second squared on bottom is going to cancel the second squared on top. And we're going to be left with units of just meters. Is that what we want? Well, we're trying to solve for delta x, or displacement. So yeah, works perfect. All right, don't forget to divide by the 1.7. All right, I'm getting 88.22 meters. Or you could say positive 88.22 meters, or you could say 88.22 meters to the right, because displacement is a vector as well. All right, that's it. So hopefully all those answers are right. Like I said, I don't have the key in front of me, but I'm pretty sure they are. So if they're not, I'll try and catch the mistake in the editing and before I put it on YouTube or whatever. All right. Anyways, those are some sample problems. If you have any questions, ask and let me know. Otherwise, have a good weekend.